So in this video, I want to address how to balance a combustion reaction that's a little more challenging than the ones that we've seen with just typical hydrocarbons. This one's with an alcohol, so you have an oxygen here and there, and that you'll see it's just a little more complicated. Now, I've gone ahead and just sort of pre-filled in everything in terms of the initial counts of the different elements. One thing I'm going to say is just take it as you see it, okay? Just do one atom at a time, ignoring all the others while you're working through initially, okay? And what I mean by that is I look at my carbons, they're fine. Hydrogen, no, they're not. I need to increase on this side, so I need a 2 in front there. So 2 times 2, that gives me 4 now total. And, first inspection, you may say, oh, 1, 4, 3, 1, 4, 3, I'm done. But notice that, and this is a common theme here, that you change one coefficient and you've affected 2 elements. So I no longer have 3 over here. In reality, 1 times 2, I got 2 oxygens here, 2 more there, and so I have 4 there. That's okay. Again, let me just keep moving on. Okay, I'm going to focus on my oxygens here, and I'm going to increase on this side. Now, at this point, there's actually a couple ways that you can approach this. You can just go in and modify this one. If you add 2 here, that would give you 4 oxygens. And then you go in and you fix carbon and hydrogen because they would be messed up. That's one way to do it. I'm going to show you another way to do this. And what I want to do is I want to focus on changing the oxygen. Is there a single number that I can put here to where I can get 4 oxygens total on this side? Well, I have 1 oxygen here, and that means that is there a way that I can just generate 3 oxygens from my diatomic element? And I'm just going to share with you what I'm thinking of, 3 halves. But I just want you to appreciate the mathematics of what I'm looking at here. Again, 1 oxygen. And then what if I take, 3 halves times 2? What happens here is basically, well, let's just do that. What happens when you do this? Right, 2 cancels out. I get 3. I have 3 oxygens here. 3 plus 1, that's 4. 1, 4, 4, 1, 4, 4. So technically, this is a balanced equation. Right? Now, it's not finished, but it is balanced. The reason why I say it's not finished is because we just don't leave a fraction sitting here. But I'm just playing games with mathematics, if you will. And by inserting that fraction, I do balance it out. It's just, it doesn't look right. To get rid of the fraction here, what we're going to do is we're going to multiply the entire expression by 2. So 1 times 2, that's 2. 3 halves times 2, that's 3. 1 times 2 is 2. And then 2 times 2 is 4. Now, let's go back and just check to see if our work is correct. Now again, before I multiplied by 2, I knew everything was balanced. Just check. Yeah. Okay, so what carbons do I have? 2 times 1, I got 2 carbons here. In terms of total hydrogens, 3, 4 times 2, there's 8 there. And then for oxygens, 3 times 2, there's 6 here, plus 2 more, there's 8 there. Okay, so now on this side, carbon times 1 times 2 is 2. Hydrogen, 2 times 4, that's 8. So far, so good. Now with oxygen, 2 times 2, that's 4 oxygens here. And then 1 times 4, that's 4 oxygens as well. Notice 4 plus 4, that's 8. There we go. If you can get comfortable using this fraction, it actually shows up in a lot of examples for reactions, especially reactions dealing with diatomic elements like oxygen. And combustion is a perfect example of that. Again, there is another way to do this. I think it's more complicated. I'm going to leave it at that. Thanks.